Google built a demo e-commerce app with 11 microservices: Go, Python, Node.js, C#, Java. It runs perfectly on their own cloud. This video is about taking that application, not touching a single line of its code, and building a complete production AWS platform around it from scratch. Terraform, EKS, ECR, Helm, GitHub Actions, all of it. This is what that looks like. This is Google Online Boutique, their own open-source microservices demo. 11 services across 5 programming languages. It has a real front-end, a real cart, a real checkout flow. It is not a toy app. Google uses it internally to test their own cloud infrastructure. The reason this is useful for us is that it already behaves like a real production e-commerce system. Multiple services, inter-service communication over gRPC, a Redis cache for the cart. Our job is not to build the application. Our job is to build everything around it. The infrastructure, the deployment pipeline, the registry, the cluster. The application code stays exactly as Google shipped it. Here's the full flow. Deploy path first. A push to main triggers GitHub Actions, which requests a short-lived OIDC token and exchanges it with AWS STS for temporary credentials. No stored AWS keys anywhere in GitHub secrets. Those credentials assume one IAM role, scoped to 2 things: pushing images to ECR and deploying to EKS. Now traffic path. A request hits the front-end external load balancer, a plain Kubernetes load balancer service, not an ALB ingress, since that controller is provisioned but not installed this run, and lands on the front-end pod. From there, front-end fans out. Cart service reads and writes the Redis cache, checkout service calls payment service, shipping service, currency service, and email service to complete an order, plus direct calls to product catalog service, recommendation service, and ad service. Underneath all of it, the EKS node group, 2t3.small instances, is what actually runs every one of those 11 pods. The control plane only schedules, it doesn't host workloads itself. And every image running on those nodes came from one of 12 ECR repositories, 1 per service. Last piece, Terraform's own state, the record of what it created, lives in S3 with a DynamoDB lock table, so 2 people can't apply at the same time and corrupt it. 110 resources, 1 apply. 7 Terraform files. Each one has a specific job. VPC, we need our own network. 3 availability zones, public subnets for the load balancer, private subnets for the EKS nodes. Nothing in the private subnet is directly reachable from the internet. EKS, version 1.30, 2t3.small nodes, cluster name Online Boutique Production. ECR, 12 private repos, 1 per service, image scanning enabled on every push. IAM, this is important. Every pod that needs AWS access gets its own IAM role through IRSA. No node-wide permissions. If one pod is compromised, it cannot access what another pod owns. Backend, Terraform state lives in S3, locked with DynamoDB so 2 engineers cannot apply at the same time. 110 AWS resources. 1 Terraform apply. Every push to main triggers the pipeline automatically. GitHub Actions builds each service, multi-stage Docker builds, so the final image only contains what needs to run, not the build tools. Images get tagged and pushed to ECR. Then Helm upgrades the release on EKS. kubectl verifies the rollout completes before the pipeline marks green. The most important part of this pipeline: there are no AWS access keys stored anywhere. Not in GitHub secrets, not in environment variables. GitHub generates a short-lived OIDC token, AWS trusts it, and assumes the deploy role directly. When the pipeline finishes, that token is gone. This is how production CI/CD should work. This is eks.tf. The node group config sets instance_types to a variable, on this deployment, that resolves to t3.small. Not a random choice. This AWS account is restricted to free-to-eligible instance types, and t3.small, 2 vCPU, 2 GB of RAM, is the smallest one that comfortably runs all 11 lightweight services. Minute size 2, max size 4, desired 2. AMI type is AL 2023 standard. No explicit disk size override here, so it uses the module's default. Now the IRSA setup. Enable _IRSA equals true turns on the cluster's OIDC provider, which is what lets a Kubernetes service account assume an AWS IAM role directly. Look at the eks.tf IRSA role block below it. That role is scoped to exactly one namespace and one service account. Kubesystem eks.tf controller SA. Nothing else can assume it. Compare that to the node role a few lines up, which has Amazon EC2 container register read-only attached directly. That one IS node-wide, because every pod on every node needs to pull images regardless of which service it is. IRSA is for the AWS access that should not be shared across every pod on a node. Getting that distinction right is most of what production IAM design actually is. This workflow triggers on push to main, on version tags, or manually via workflow dispatch. Look at the permissions block, ID token, right. That one line is what lets this workflow request an OIDC token from GitHub in the first place. Without it, none of the AWS steps below would even be able to authenticate. Now the credentials step, role to assume, pointing at the deploy role ARN, plus the AWS region. That's it. No AWS access key ID. No AWS secret access key. In plain terms, here's what happens. GitHub generates a short-lived token proving exactly which workflow, in which repo, is running right now. AWS's IAM trusts that token. The trust policy on this role is scoped to this specific repository, and in exchange issues temporary AWS credentials for this job only. When the job ends, those credentials are gone. Nothing to rotate, nothing to leak. And look at the build job above it. 12 services in the matrix, fail fast, false, which means all 12 build and push to ECR in parallel, not one after another. This file doesn't replace the base values.yaml. It layers on top of it. You pass both with 2 F flags, and whatever's here overrides whatever's in the base chart. First thing worth seeing, images.repository points at an ECR registry URL, not Docker Hub. Every image this cluster pulls comes from our own private registry. Below that, every service has its own resource block, requests and limits. Recommendation service asks for 220 megs. Checkout service only asks for 64. These aren't copy-pasted defaults. They matter because the scheduler uses the request value to decide which node a pod can even fit on. And the service accounts block carries an IRSA annotation, eks.amazonaws.com/role-an, wired to the ECR pull role, applied to every service's service account. This is the actual repo. Terraform AWS is everything that provisions the infrastructure. The add-ons folder has the ALB ingress controller, external DNS, and cluster autoscaler, provisioned but not installed in this deployment. Kubernetes manifests AWS has the HPA configs and node affinity patches. The GitHub Actions workflow is one file, AWS eks.deploy.yaml, and it handles the full build, push, and deploy. Clone this, fill in your AWS account ID in Terraform.tf files. Then cd into Terraform AWS Bootstrap and run Terraform init and Terraform apply to provision the state backend first. 2 nodes. Ready. 11 pods. 11 running. 1 Helm release. Deployed. This single release manages all 11 services, every deployment, every service, every config map. Upgrade or rollback with one command. This is running on real AWS infrastructure. Real EKS nodes in US East 1. Real ECR images. The URL you are looking at is a Kubernetes load balancer service endpoint. AWS provisioned this automatically when we deployed. Open a product. Add it to the cart. That cart request hits the front end, which calls cart service, which writes to Redis. All of this is running across 2 T3.small nodes, deployed with a single Helm upgrade command. 6 production skills in one project. Terraform, not just writing it, but structuring it with a remote state backend and module separation. EKS, real cluster, real workloads, not a local minikube setup. GitHub Actions OIDC, keyless CI/CD, the way enterprise teams actually do it. Helm, one release managing 11 services. IRSA, least privilege per pod, not per node. ECR, private registry with scanning. This is the foundation every DevOps engineer needs before they can work on AI infrastructure, platform engineering, or any production system. Full repos linked below. Next, can this handle 100,000 users? We're load testing it.